What kind of function are each of these pieces? Like, what kind of function is x squared plus 1?
Quadratic.
It's a quadratic, good. And more generally, it's a polynomial, right? What do we know about polynomials? What can we say about the continuity of a polynomial? Are polynomials continuous?
Polynomials aren't polynomials continuous for everything except 2 points?
What do you mean by,
Or like,
by everything except
never mind. I'm probably referring to something else.
Polynomials are continuous everywhere, right? So notice here, each piece is a polynomial. And we know that polynomials are continuous everywhere. That was a theorem that we showed last time. So where's the one point that we have to consider in this case where there could potentially be a point of discontinuity for this function here?
Zero.
Good. So at x equals 0, we notice that the two functions are or where x equals 0 is where the two graphs sort of change from one piece to the next, right? So we have the only point to consider here where there could potentially be a point of discontinuity is at x equals 0. Right, in other words, where the function changes from when the function changes from the top piece to the bottom piece. Okay, so that's the only possibility. So what we should think about is our continuity checklist. Remember, so let's go through the checklist at x equals 0. First, we'll check, does the function at 0, can we get a value there? What's f of 0 in this case?
1.
Good. In other words, you plug 0 into the top piece, right? Because you get, when x is equal to 0, right? We're going to plug it into the top piece. So we get a value there, right? The next thing to think about, what do we get when we try and take the limit as x approaches 0? So here maybe it's worth considering the left and the right. So to answer this question here, let's look at the left and the right side limits. So taking the limit as x approaches 0 from the right, and taking the limit as x approaches 0 from the left. Okay. So what might help here is to think about which piece am I evaluating on if I'm approaching from the right? Am I using the top piece or the bottom piece?
The bottom piece, because
X has to be greater than 0.
Yes, exactly. Very good. So when x is greater than 0, right, we're approaching from the right. So when x is greater than 0, we're going to use the bottom piece. And so now evaluating 3x plus 5 at 0, we get, what do we get?
5.
5, good. On the other hand here, it looks like if we were to approach from the other side, now I'm going to use the top piece because that's when x is less than 0, we're going to use the top piece. So now evaluating this guy at 0, we get 1. So what does that tell us here?
That they are, that there's a jump discontinuity.
Okay, so in other words, it's approaching one thing from the left and a different thing from the right. So we get the limit as x approaches 0 does not exist. Right, we have a jump discontinuity at x equals 0. Okay, so it'll be continuous everywhere except at x equals 0. So to answer the question, what intervals will f of x be continuous on? Well, it'll be continuous for every value of x except 0. So it'll be continuous from negative infinity to 0, and then from 0 to infinity. So basically everywhere except for 0. Okay, and here we can kind of see in this picture what's happening, right? From the left side, it's approaching 1, and then from the right side, it's approaching 5. And so there's a jump in the graph. Okay. And actually notice here that they're looking at the two pieces as separate functions. Like for instance here, the left piece is continuous on the interval from negative infinity to 0, including 0, because it's continuous at the right, or it's continuous from the left there. But here it's continuous on the open interval from 0 to infinity. Okay, so anyway, that's kind of actually looking at those two pieces separately. So that's not quite what I was doing, but yeah, I would actually state the question differently if that's what I was looking for. But do you guys have questions about that? So let's look at another, well, actually in this case, we're updating one of our limit laws, which, let me see here. So yeah, so recall the limit law that the limit as x approaches a of f of x to the 1 over n is equal to the limit as x approaches a of f of x, and all of that raised to the 1 over n power. As long as the function is positive for x that are close to a when n is even. Okay, so if f is continuous at a, what can be said about the continuity of f of x to the power of 1 over n at a? Okay, so let's think about that. If n is odd, and here if we know that f is continuous at a, remember that we unpack what that means. It means that the limit as x approaches a of f of x is equal to f of a. So if that's true, and if n is odd, then the limit as x approaches a of f of x to the 1 over n is equal to oops, not there, 1 over n. So that's just using that limit law there. And here we don't need to worry about f being positive because when n is odd, it'll always be this way. And then we said here, because f is continuous at a, then the limit as x approaches a of f of x is equal to f of a. Okay, and there we have it. So this shows that when I put a power there, f of x to the 1 over n is continuous at a. And on the other hand, if n is odd, if n is even, then we need to assume that f of x is greater than or equal to 0, like what we were saying here. So this requires the assumption that f of x is greater than or equal to 0 in some region around a. And moreover here that then this would equal to f of a to the 1 over n with that extra assumption. Okay. So in other words, if I have like a square root, for instance, 1 over n would be like a half power. If I have a square root, then we need it to be positive inside the square root in order to say it's continuous. And yeah, so that's what this theorem is saying here.
So does that mean that it's going to be continuous at negative infinity to positive infinity?
If it's an odd power, then yes, or if it's a 1 over n where n is an odd power, then it will be continuous on that interval. But because here, if I have a 1/2 power, then it'll only be continuous on the interval when f of x is positive.
So, or 0 to infinity?
Let's take an example. Suppose I have just the square root of x plus 3, right? Where is this continuous?
Is 0 to positive infinity?
Actually, more than that. So it'll be
would it be
continuous as
negative
long
3?
as x plus 3 is greater than or equal to 0. So as long as x is greater than or equal to negative 3. So here you would see it's continuous on the interval from negative 3 to infinity. Okay, does that make sense?
Yeah. Yeah, it does.
Okay, so yeah, as long as the value underneath the square root is greater than or equal to 0, then you know it's continuous on that interval. Or here, let's look at a couple other examples. I think these ones also kind of demonstrate the idea also. So let's take the function square root of 9 minus x squared. So again, the same idea, as long as 9 minus x squared is greater than or equal to 0. By the way, what interval would this 9 minus x squared be greater than or equal to 0? What interval would that be on? So like if I say, okay, let's
Would be
move
3.
x
-3, +3.
Yeah, good. So if x squared is less than or equal to 9, right? Then I can square root both sides. But here, when I take the square root of x squared, then I have the absolute value of x is less than or equal to 3. So therefore, 3 is between, or sorry, x is between -3 and +3. Okay, so this will be continuous on the interval -3 to 3. Oops. You guys know what kind of graph this is? Or what kind of shape this graph is?
A cube root graph or no?
Not quite.
I believe that's linear.
Not quite.
It goes out exponentially towards the positive x. But in this case, it's between -3 and 3.
Not quite. Here's a hint. Here's a hint. If I write y equals 9 minus x squared, and then I square both sides.
Oh, parabola.
Not
That's
quite.
an upside down parabola.
Not quite. So if I square both sides, then I get y
It's the
squared
square root
equals 9 minus.
function.
So if I add the x squared over here, what is this?
Oh, circle.
That is a
Circle.
Ellipse or
It's a circle actually. It's almost like an ellipse, but it's a circle. So it's a semicircle actually, right? Because it's the positive side of the y-axis.
True.
It's a circle with a radius of 3, like this.
so half a circle?
Yep, it's a semicircle.
Okay.
And that makes sense now that it's continuous on -3 to 3 because of course our circle doesn't go beyond those points, right? Okay, so what about this one here? I've got the f of x equals x squared minus 2x plus 4. We've got this polynomial, and then it's raised to the 2 over n power, or 2 over 3 power, I should say. Now notice it's got the 2 over 3 power. It's not an even power in the denominator there. So is this one? So if I've got like a 2 over 3 power, think of this as like a 1 over 3 power on the whole thing, right? So it's like a cube root here, right? So you've got the odd index root. So that means you can take the odd index root of any real number. So there's no restrictions on anything here. And in fact, even still, if this were an even root, I think you would still have a positive value in here. But anyway, so with that, because it's an odd index root here, you can take the 1 over 3 power of any real number. Whether it be positive or negative, right? It's like the cube root. So this one's continuous for all x. Okay. Does that make sense?
Could you explain it a little bit better? Not better, but I mean, could you explain it a little bit further? I'm sorry.
So, okay, let me go back to the previous thing here. Okay, so, and in fact, what we proved here is that if I have a cube root, like if I have an odd degree power, this is continuous for any a. Because f of x could be positive or it could be negative, doesn't matter. If I take the cube root of any real number, it always works. I can take the cube root of any positive number, or I can take the cube root of any negative number, and I always get an answer, right? That's not the same with the square root, though. Okay. So just remember, if this is an odd index root, if I had like the 1/7 power, it'd be the same thing as 7th root. You can take the 7th root of any real number. So it doesn't matter what's inside here. This can be anything. And it'll always be continuous. As long as this is continuous inside here, which of course it is. It's a polynomial. Polynomials, we know, are always continuous everywhere. So then raising a polynomial to a 1/3 power is still continuous everywhere.
Oh, okay, thank you.
Because it's the odd index root. If this were a 1/2 power or a 1/4 power, then it would be a different story. Okay, so let me. Oh yeah, so here's the graph of or a semicircle, right? Yeah, this one we don't need to worry about a graph just because it's, we know it's a polynomial raised to the 1/3 power, so it'll be continuous everywhere. And here we're looking at the continuity of trigonometric functions, which is somewhat straightforward if we think about just the way we've looked at the sine and the cosine graph, right? Those are always continuous for all x. And if we have other graphs, like the secant graph here has a bunch of vertical asymptotes, so as long as you're not at one of the points where there's a vertical asymptote, it'll be continuous. So yeah, if I have sine or cosine or tangent, cosecant, cotangent, they'll be continuous at all the values of x in their domains. Which means, okay, as long as, so we know sine and cosine, x, the domain is all real numbers. The other graphs, though, have different domains. The other ones have restrictions. Where they have, so yeah, the others have restrictions on the domains where they have vertical asymptotes. So like where, tan is, sine over cosine, right? It'll have vertical asymptotes where cosine is equal to 0, right? Same for the other ones, but anyways, let me see. If, oops. If we can just try out an example here.
Professor, I had a question.
Yes.
You said tangent had a vertical asymptote at x equals 0, correct? Oh, I guess a y or x equals 0. Oh, and cosine equals 0. Okay, okay, never
Yeah.
mind. I didn't read
Remember,
that part.
so if it's 0 in the denominator, that's when we're going to have vertical asymptotes, right? So for
Yeah.
tangent, it's at like pi over 2, right? Or negative pi over 2, or 3 pi over 2, or negative 3 pi over 2, and so on, right?
Yeah, that makes sense now. Thank you.
So actually, there's infinitely many vertical asymptotes in our graph of tangent, but they have this sort of predictable pattern that we can use to find them. But sine and cosine by themselves are always continuous, but let's look at just an example with thinking about evaluating a limit like this. We've kind of seen examples like this in the past, but what do you guys think we could do if I wanted to evaluate this one? Any ideas?
Change the top to sine squared, I think.
That that would be possible. You could change it to negative sine squared actually, but maybe not. That maybe not exactly helpful as far as getting it into a form where we can evaluate. Think of it this way: we want to be able to evaluate it at x equals 0, and the problem is that right now I'm getting 0 in the denominator, right? Because cosine of 0 is 1, right? So if I just plug in 0 here, I get 1 minus 1 is 0 in the denominator.
Can you do like the a squared minus b squared for the numerator?
Okay, that sounds like a good idea. So remember, like if we're in this, it's like if I've got u squared minus 1, right? We can do u minus 1, u plus 1, right? So it's basically a difference of squares form up here. So how do I factor cosine squared minus 1?
It's just going to be cosine minus 1 and cosine plus 1.
Very good. And now it simplifies, right? That guy divides. And now I can evaluate it. And then here, yeah, cosine of 0 is 1. And so we get 2. Okay. So just a little factoring trick there was helpful. Do you guys have any questions about that? You guys are good with that? Okay, so let me see. We got maybe a couple more here. Okay, I'm going to introduce the intermediate value theorem here and then just give you guys a quick little example of it. But then that'll be probably where we'll have to leave it for today because I want to give you some time to take your quiz. But let's just read, well, okay, so I'm going to look at the picture and then we're going to read the theorem and try and make sense of what the theorem says and relate it to the picture. So in my opinion, the picture kind of explains the theorem a lot better. Okay, so suppose we have a continuous function on some closed interval from a to b. And then I pick any value that's in between the interval f of a to f of b. So say I pick some value L. Then I know that that value of L will correspond to some point on the graph at C where C is between A and B. So one way to interpret this theorem is that if I have a continuous function, it's gonna hit all the intermediate values between f of A and f of B. Okay. Same idea here. I've got some continuous function on the interval from A to B. And the graph of my f of x is going to hit all the values that are in between f of A and f of B. So if I pick any L, any number that's in between f of A and f of B, I know my graph is going to hit it at least once. And in this case, we see it actually hits it 3 times. So there's at least one C. In this case, there's 3 C's where f of C is equal to L. Okay, so that's the picture. I think it makes a lot of sense when you look at the picture because it's clear that if I draw a continuous graph, it has to, be one connected piece. So it's going to hit all the values in between f of A and f of B. It's never going to go outside of, or it's never going to skip over any points, right? So that's all the intermediate value theorem says. And the way we state it, it says, suppose f is continuous on the interval from A to B, and L is some number that's between f of A and f of B. Then there is at least one number C in the interval AB where f of C equals L. Right? So again, it's just saying that if I've got some function that's continuous on the interval from A to B, okay, its graph has to look something like that. And then here's f of A here, and here's f of B here. So if I pick some random number in between them, then it's got to correspond to some point C in the interval A to B, where f of C is equal to L. Okay. That's all it says. Nothing crazy, but I think what's confusing about it is just the way it's worded. So in my opinion, thinking about the picture here makes it easier to interpret what this theorem is saying. Okay. So do you guys have questions about the theorem or what the theorem is saying? I know it's kind of hard to wrap your head around it, just the way it's worded, but we can do one quick example of it. And here's a picture of what it looks like if I don't have a continuous function. You see that it's not necessarily going to satisfy that theorem, right? So you see the intermediate value theorem does not apply when f is not continuous. Because here we've got a jump in the graph. And so because there's a jump there, it doesn't hit all of the intermediate values that are in between f of A and f of B. So I can pick some number here, L, that's in that gap. And so we see that there's no point C where f of C is equal to L.